Tonight, we're going to talk about something that breaks the laws of physics. A monster so impossibly massive that scientists still can't explain how it exists. It's called TON 618, and it's the largest black hole ever discovered in the universe. When astronomers calculated its mass for the first time, they thought they made a mistake. Then they checked again, and again, because what they found defies everything we understand about how black holes form and grow. This thing shouldn't be possible, yet there it is, lurking in the depths of space, challenging every theory we've built about the cosmos. By the end of tonight, you're going to see why this single object is forcing us to rewrite the rules of the early universe, and why some physicists believe it might be proof that our theories about cosmic evolution are completely wrong. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with a story that begins in 1957. Astronomers were conducting a radio survey of the sky, mapping out sources of radio waves coming from deep space. This wasn't glamorous work. It involved hours of patient observation, pointing radio telescopes at different patches of sky, recording signals, cataloging data. The technology was primitive by today's standards. Radio astronomy itself was still a relatively new field, having only emerged after World War II, when scientists repurposed military radar technology for peaceful purposes. The astronomers working on this survey had no idea what most of the radio sources they were detecting actually were. They just knew something out there was emitting radio waves, and they were determined to catalog every source they could find. Among the thousands of radio sources detected, one stood out. It was located in the constellation Canes Venatici, a relatively faint constellation in the northern sky. The radio signal from this particular source was unusually strong, far stronger than most of the other sources they had mapped. They gave it a designation, a catalog number, that would become famous decades later, TON 618. The name came from the Tonantzintla Observatory in Mexico, where the survey was being conducted. At the time, the astronomers had no way of knowing what this object was. When they turned optical telescopes toward the coordinates, they saw almost nothing. Just a faint blue point of light, so dim that it was barely visible even with the best telescopes available at the time. This was puzzling. Why would such a faint optical source produce such powerful radio emissions? It didn't match any known type of star or galaxy. The mystery deepened when astronomers measured the spectrum of light coming from TON 618. Spectroscopy is one of the most powerful tools in astronomy. By splitting light into its component wavelengths, astronomers can determine the chemical composition, temperature, and motion of distant objects. When they analyzed the spectrum of TON 618, they found something extraordinary. The spectral lines, the characteristic patterns that indicate the presence of specific elements, were shifted dramatically toward the red end of the spectrum. This redshift is caused by the expansion of the universe. As space itself expands, it stretches the wavelength of light traveling through it. The greater the distance, the more the light is stretched, and the larger the redshift. The redshift of TON 618 was enormous. It was so large that it immediately told astronomers this object was incredibly far away, billions of light-years distant, existing at a time when the universe was much younger. But if it was that far away, how could it be bright enough to detect at all? For TON 618 to be visible from such an enormous distance, it had to be producing an absolutely staggering amount of energy. More energy than entire galaxies. For years, astronomers debated what TON 618 could be. Some thought it might be a strange type of star. Others suggested it could be a galaxy undergoing some kind of explosive event. The truth wouldn't become clear until the 1960s and 70s, when astronomers began to understand a new class of objects called quasars. Quasars, short for quasi-stellar radio sources, were mysterious objects that looked like stars through optical telescopes but emitted enormous amounts of radio waves and light. As more quasars were discovered and studied, astronomers realized they weren't stars at all. They were the incredibly bright cores of distant galaxies, powered by supermassive black holes consuming vast amounts of matter. The light and radio waves weren't coming from the black holes themselves, which emit no light, but from the superheated material swirling around them in massive accretion disks. TON 618 was one of these quasars, but it would take decades more before astronomers could determine just how special it really was. The technology needed to measure the mass of the black hole powering TON 618 didn't exist yet. Astronomers had to wait for better telescopes, better spectrographs, better computer models. Throughout the 1980s and 90s, as technology improved, astronomers began to measure the masses of black holes powering various quasars. They did this by studying the motion of gas in the accretion disk and the surrounding galaxy. By applying the laws of gravity and orbital mechanics, they could calculate how massive the central black hole must be to produce the observed motions. When they finally turned their attention back to TON 618, applying these new techniques, the results were shocking. The initial calculations suggested a mass of around 40 billion solar masses. This was already extraordinary, making it one of the most massive black holes known. But as observations improved and more data was collected, the estimates kept going up. 50 billion solar masses. 60 billion. By the early 2000s, astronomers had refined their measurements enough to confidently state that TON 618 weighs approximately 66 billion times the mass of our Sun. This made it the most massive black hole ever discovered. Even today, decades after its initial discovery, TON 618 remains the heavyweight champion of black holes. A few other candidates have been proposed as potentially more massive, but none have been confirmed with the same level of certainty. TON 618 stands alone as the largest, most massive, most powerful black hole we've ever found. To understand how absurd this number is, we need to start with something familiar and work our way up. This is the only way the human brain can even begin to grasp numbers this large. Our minds didn't evolve to comprehend cosmic scales. We're built to understand the size of trees, the weight of rocks, the distance to the next valley. When we start talking about billions and trillions, these numbers become abstract, meaningless. So we have to build up slowly, step by step, letting each level of scale sink in before moving to the next. Let's begin with Earth. Our planet, the only home humanity has ever known, weighs about 13 trillion pounds. That's 13 followed by 24 zeros. In scientific notation, that's 1.3 times 10 to the 25th power pounds. It's a number so large that it's hard to visualize. If you tried to count to 13 trillion, counting one number per second, it would take you longer than the current age of the universe. Trillions of times longer. Earth contains everything we've ever known. Every mountain, every ocean, every forest, every city. All 7.8 billion people currently alive, plus all the humans who've ever lived throughout history. Every animal, every plant, every microorganism. The entire mass of life on Earth, what scientists call the biosphere, weighs about 1.2 trillion pounds. That's just 1/12 trillionth of Earth's total mass. The oceans, which cover 71% of Earth's surface, weigh about 3 trillion pounds. The atmosphere, all the air surrounding our planet, weighs about 11 quadrillion pounds. The crust, the rocky outer shell we live on, varies in thickness from about 3 miles under the oceans to about 45 miles under the continents, and it weighs approximately 56 trillion pounds. But most of Earth's mass isn't in the crust or the oceans or the atmosphere. It's in the mantle and core. The mantle, a layer of hot, flowing rock extending from just below the crust down to about 1,800 miles deep, makes up about 84% of Earth's volume. The core, split into a liquid outer core and a solid inner core, is mostly iron and nickel, compressed under enormous pressure and heated to temperatures exceeding 9,000 degrees Fahrenheit. All of this combined, 13 trillion pounds, and yet in cosmic terms, Earth is insignificant, a speck of dust, a rounding error. Now let's jump to the Sun. Our Sun is the anchor of the solar system, the source of virtually all energy on Earth. It's been burning for about 4.6 billion years and has enough fuel to continue for another 5 billion years before it exhausts its hydrogen and begins its death throes. The Sun is so massive that it contains 99.86% of all the mass in our solar system. Think about that for a moment. Jupiter, the largest planet, weighs about 300 times the mass of Earth. Saturn, with its spectacular rings, weighs about 95 times Earth's mass. Neptune, Uranus, all the other planets, all the moons, all the asteroids, all the comets, all the dust, all the gas, everything in the solar system except the Sun adds up to just 0.14% of the total mass. The Sun alone weighs about 4.4 nonillion pounds. That's a 4 followed by 30 zeros, or about 333,000 times the mass of Earth. To put it another way, you could fit about 1.3 million Earths inside the Sun's volume. The Sun is so large that if it were hollow, you could drop 1 million Earths into it and still have room left over. Every second, the Sun converts about 600 million tons of hydrogen into helium through nuclear fusion. This process releases energy in the form of light and heat, energy that takes about 8 minutes to travel the 93 million miles from the Sun to Earth. The amount of energy the Sun produces every second is equivalent to exploding 92 billion megatons of TNT. For comparison, the largest nuclear weapon ever detonated, the Soviet Tsar bomber, had a yield of about 57 megatons. The Sun produces the equivalent of 1.6 billion Tsar bombers every single second, and it's been doing this for 4.6 billion years. The Sun is a massive, incredibly powerful object. It's the center of our world, the reason life exists on Earth. Without the Sun, Earth would be a frozen, lifeless rock drifting through space. But even the Sun, massive as it is nothing compared to what lurks at the center of our galaxy. At the heart of the Milky Way, about 26,000 light-years from Earth, sits a supermassive black hole called Sagittarius A star. We can't see it directly because black holes don't emit light, but we can see its effects. Astronomers have been tracking the motion of stars near the galactic center for decades, and what they've observed is extraordinary. Stars whip around an invisible point at incredible speeds, sometimes reaching velocities exceeding 5,000 miles per second. That's fast enough to circle the entire Earth in about 5 seconds. These stars are orbiting something incredibly massive, something compact enough that it must be a black hole. By tracking the orbits of these stars, astronomers can calculate the mass of the object they're orbiting. The answer is about 4 million times the mass of our Sun. 4 million suns, compressed into a region smaller than our solar system, creating a gravitational well so deep that not even light can escape once it crosses the event horizon. Sagittarius A star is enormous by human standards. Its event horizon has a diameter of about 14 million miles. That's roughly 16 times the diameter of the Sun. If you replaced our Sun with Sagittarius A star, the event horizon would extend about halfway to Mercury's orbit. It would dominate the inner solar system, a dark sphere of nothingness where our sun once shone. Any planet that crossed the event horizon would be doomed, falling inevitably toward the singularity at the center. The gravity near Sagittarius A star is so intense that it warps space-time dramatically. Time itself slows down near the event horizon. If you could somehow survive close to Sagittarius A star and spend 1 hour there, years would pass for someone far away from the black hole. This isn't science fiction. This is a real consequence of Einstein's general relativity, confirmed by countless observations and experiments. Gravity doesn't just pull on objects. It warps the fabric of space-time itself, and in extreme gravitational fields like those near a black hole, these effects become dramatic and impossible to ignore. Sagittarius A star controls the motion of hundreds of billions of stars in our galaxy. The Milky Way is a spiral galaxy, and that spiral structure exists because of the way stars orbit the galactic center. Everything in the galaxy, including our Sun and our solar system, is orbiting Sagittarius A star. We're traveling at about 500,000 miles per hour, relative to the galactic center, completing one full orbit every 230 million years. The last time our solar system was in its current position relative to the galactic center, dinosaurs were just beginning to evolve on Earth. Sagittarius A star is the anchor of our galaxy, the invisible hand that keeps everything spinning in its cosmic dance. It's a monster, a titan, an object of such immense mass and power that it defies everyday comprehension. And yet, compared to Ton 618, Sagittarius A star is nothing, a speck, a tiny, insignificant object. Ton 618 weighs 16,500 times more than Sagittarius A star. 16,500 times. Let me repeat that because it's important. Take the supermassive black hole at the center of our galaxy, the object that controls the motion of hundreds of billions of stars, the gravitational anchor of the entire Milky Way. Now multiply its mass by 16,500. That's Ton 618. It's not just bigger. It's bigger in a way that makes Sagittarius A star look small by comparison. If we could somehow replace Sagittarius A star with Ton 618, the consequences would be catastrophic beyond imagination. The gravitational effects would be felt thousands of light years further out than they currently are. Stars that currently orbit safely at distances where they're under no threat would suddenly find themselves in danger zones. The gravity would reach out, pulling harder, accelerating orbits, disrupting the delicate balance that keeps the galaxy stable. Stars near the galactic center would be ripped apart by tidal forces, torn to shreds as they cross too close to the event horizon. Entire star systems would be consumed, swallowed whole, their matter added to the black hole's already incomprehensible mass. The structure of the Milky Way itself would change. The spiral arms might be disrupted or destroyed. The rate of star formation would plummet as gas clouds, the raw material for new stars, were either consumed by the black hole or ejected from the galaxy entirely by the powerful jets. Within a few million years, the galaxy would be unrecognizable, and within a few 100 million years, it might cease to exist as a coherent structure at all, torn apart by the immense gravitational forces. This isn't speculation. This is what physics tells us would happen if you dropped a black hole as massive as Ton 618 into the heart of our galaxy. The good news is that Ton 618 is very, very far away. The bad news is that its existence at all tells us something disturbing about the universe. But it gets even more mind-bending when we talk about size. And this is where Ton 618 truly becomes incomprehensible. Black holes are defined by their event horizon, the boundary beyond which nothing, not even light, can escape. The event horizon isn't a physical surface like the surface of a planet or a star. It's a mathematical boundary, a point of no return defined by the strength of gravity. Cross the event horizon, and you're doomed. There's no escape, no turning back, no possibility of rescue. Every path you could take, every direction you could move, leads inevitably toward the singularity at the center. For a black hole, size is measured by something called the Schwarzschild radius, the distance from the center to the event horizon. The Schwarzschild radius depends on mass. The more massive the black hole, the larger the event horizon. This relationship is actually surprisingly simple. Double the mass, and you double the Schwarzschild radius. Make it 10 times more massive, and the event horizon becomes 10 times larger. For a black hole with the mass of our Sun, the Schwarzschild radius is about 1.9 miles. That means if you somehow compress the entire Sun down into a sphere less than 4 miles across, it would become a black hole. Everything within 1.9 miles of the center would be inside the event horizon, unable to escape. Obviously, this is impossible to do. The Sun doesn't have enough mass to collapse into a black hole naturally. When it dies, about 5 billion years from now, it will expand into a red giant, shed its outer layers, and leave behind a white dwarf, a dense ember about the size of Earth. But if you could magically compress the Sun, or if the Sun had been born with more mass, it could form a black hole, and that black hole would have an event horizon less than 4 miles across. For stellar mass black holes, the ones formed when massive stars explode in supernovae and their cores collapse, the event horizons are typically between about 6 miles and 60 miles in diameter. These are small by cosmic standards. You could fit a stellar mass black hole comfortably within a city. Supermassive black holes are different. They're millions or billions of times more massive than stellar black holes, and their event horizons are correspondingly larger. Sagittarius A star, with its mass of 4 million suns, has an event horizon with a diameter of about 14 million miles. That's large, very large. To put it in context, the diameter of the Sun is about 864,000 miles. So the event horizon of Sagittarius A star is about 16 times larger than the Sun. If you replaced the Sun with Sagittarius A star, Mercury, the closest planet to the Sun, would still be safe. Mercury orbits at an average distance of about 36 million miles. The event horizon of Sagittarius A star would extend to about 7 million miles, well short of Mercury's orbit. Venus, Earth, Mars, all the planets would survive, at least initially, though their orbits would be disrupted by the change in the Sun's mass. Sagittarius A star's event horizon, while enormous compared to stellar black holes, would still fit within the inner solar system. Now let's talk about TON 618. The event horizon of TON 618 has a diameter of approximately 2,600 astronomical units. An astronomical unit, abbreviated AU, is the average distance from Earth to the Sun. It's about 93 million miles, a distance that light covers in about 8 minutes. The AU is a convenient unit for measuring distances within the solar system. Mercury orbits at about 0.4 AU. Venus at about 0.7 AU. Earth, by definition, at 1 AU. Mars at about 1.5 AU. Jupiter at about 5 AU. Saturn at about 9.5 AU. Uranus at about 19 AU. Neptune at about 30 AU. And Pluto, though no longer classified as a planet, orbits at an average distance of about 39.5 AU. The Kuiper Belt, a region of icy bodies beyond Neptune that includes Pluto, extends from about 30 AU to about 50 AU. The heliosphere, the bubble of charged particles emanating from the Sun that defines the boundary of the Sun's influence, extends to about 120 AU. Voyager 1, the most distant human-made object, crossed this boundary in 2012 and is now about 160 AU from the Sun. The Oort cloud, a theoretical shell of icy objects surrounding the solar system, is thought to extend from about 2000 AU to as far as 100,000 AU. So when I tell you that the event horizon of TON 618 is 2,600 AU in diameter, you can start to grasp the scale. It's larger than Pluto's orbit, much larger. Pluto orbits at about 40 AU from the Sun. The event horizon of TON 618 extends to 1,300 AU from its center. That's 33 times further than Pluto's orbit. In actual miles, the event horizon of TON 618 stretches about 242 billion miles across. Let me give you some perspective on this distance. Light travels at 186,000 miles per second. It's the fastest thing in the universe. Nothing can move faster than light. It takes light about 1.3 seconds to travel from Earth to the Moon. It takes about 8 minutes for light to travel from the Sun to Earth. It takes about 5.5 hours for light to travel from the Sun to Pluto, but it takes over 15 days for light to cross from one side of TON 618's event horizon to the other. 15 days, more than 2 weeks. Think about what this means. If you were somehow standing on one edge of the event horizon and you shined a flashlight toward the other side, the light would take over 2 weeks to get there. If you could build a bridge across the event horizon and tried to walk from one side to the other, moving at a brisk pace of 3 miles per hour, it would take you 9 million years to cross. The event horizon of TON 618 is so vast that it makes our entire solar system look like a tiny speck. If you place TON 618 at the center of our solar system, replacing the Sun, the event horizon would swallow everything. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, Pluto, the Kuiper belt. All of it would be inside the event horizon. Voyager 1, after traveling for over 40 years and covering more than 14 billion miles, would still be deep inside the event horizon. The event horizon would extend about 40 times the distance to Neptune. It would reach well into the Oort cloud, that distant shell of icy objects that marks the outermost boundary of the Sun's gravitational influence. Everything we've ever considered part of our solar system would be trapped inside, unable to escape, doomed to fall toward the singularity. This isn't just a black hole. This is a cosmic chasm, a wound in space-time, an abyss so vast and so deep that it challenges our ability to comprehend it. And yet, as impossible as it seems, TON 618 is real. It exists. Right now, billions of light years away, it's sitting in space, warping the fabric of reality around it, pulling in matter, growing even larger. But here's what makes TON 618 truly special, truly terrifying. It's not just its size, it's when this black hole existed, and more importantly, it's how quickly it grew to reach that size. TON 618 is located approximately 10.4 billion light-years away from Earth. Now, this distance measurement needs some explanation because it's more complicated than it might seem. When we say something is 10.4 billion light-years away, we're not talking about a simple straight-line distance measured with a ruler. We're talking about light travel time. The light we see from TON 618 has been traveling through space for 10.4 billion years before reaching our telescopes. And here's the crucial part. Because light takes time to travel, when we look at TON 618, we're not seeing it as it is today, in the present moment. We're seeing it as it was 10.4 billion years ago. We're looking back in time. This is one of the strange and wonderful things about astronomy. Every time you look at a distant object, you're seeing it as it was in the past. When you look at the moon, you're seeing it as it was about 1.3 seconds ago. because that's how long it takes light to travel from the moon to Earth. When you look at the sun, you're seeing it as it was about 8 minutes ago. When you look at the nearest star system, Alpha Centauri, you're seeing it as it was about 4.4 years ago. When you look at the Andromeda Galaxy, you're seeing it as it was about 2.5 million years ago. And when you look at TON 618, you're seeing it as it was 10.4 billion years ago. The universe is about 13.8 billion years old. We know this from multiple lines of evidence, including measurements of the cosmic microwave background radiation, observations of the oldest stars, and calculations based on the expansion rate of the universe. If TON 618 is 10.4 billion light-years away, that means we're seeing it as it existed 3.4 billion years after the Big Bang. The universe, at that time, was less than 1/4 of its current age. To put this in perspective, 3.4 billion years is less time than it took for Earth to form after our Sun was born. Earth didn't come into existence until about 4.5 billion years after the Sun formed, and we're talking about a time when the universe itself was only 3.4 billion years old. The first stars didn't form until about 100 to 200 million years after the Big Bang. The first galaxies assembled over the next few hundred million years. By 3.4 billion years after the Big Bang, the universe was still very young. Galaxies were smaller and less organized than they are today. The cosmic environment was more chaotic, with more frequent galaxy mergers and collisions. Star formation rates were higher. There was more gas and dust available to form new stars. It was, in many ways, a more violent and dynamic universe than what we see today. And in that early universe, just 3.4 billion years after the beginning of everything, TON 618 already existed. Not as a small black hole, not as a modest supermassive black hole, but as a monster weighing 66 billion solar masses, already fully formed, already one of the largest black holes that would ever exist. This is the problem. This is what shouldn't be possible. According to our current understanding of physics, black holes grow through two main processes. The first is accretion, the gradual accumulation of matter. A black hole sits in space, and anything that gets too close falls in. Gas, dust, stars, planets, anything with mass that crosses the event horizon becomes part of the black hole. As matter falls toward the black hole, it doesn't just disappear quietly. It forms an accretion disk, a swirling vortex of materials spiraling inward. The friction in this disk heats the material to incredibly high temperatures, sometimes millions or even billions of degrees. At these temperatures, the matter emits enormous amounts of energy in the form of light and radiation. This is what we see when we observe quasars like TON 618. The incredibly bright light isn't coming from the black hole itself, which emits nothing. It's coming from the superheated matter in the accretion disk, matter that's about to cross the event horizon but hasn't quite reached it yet. For a brief moment, before it disappears forever, this matter shines brighter than entire galaxies. Through accretion, a black hole can grow steadily over time, pulling in more and more matter, increasing its mass. The second way black holes grow is through mergers. When two black holes get close enough, their gravitational attraction pulls them together. They orbit each other, getting closer and closer, spiraling inward until they finally collide and merge into a single larger black hole. These mergers are violent events that release tremendous amounts of energy in the form of gravitational waves, ripples in the fabric of space-time itself. In 2015, the LIGO Observatory detected gravitational waves for the first time, confirming one of Einstein's predictions and opening a new window into the universe. Since then, dozens of black hole mergers have been detected through their gravitational wave signatures. These observations have taught us a lot about how black holes merge and grow. Both accretion and mergers are real processes that we've observed and studied. They're well understood, at least in principle. The problem is, they both take time, a lot of time. And there simply wasn't enough time for TON 618 to grow as large as it did. Let's start with accretion. There's a fundamental limit to how fast a black hole can grow through accretion, called the Eddington limit. This limit is named after Arthur Eddington, the British astronomer who first described it in the early 20th century. The Eddington limit arises from a balance between two forces. On one hand, there's gravity, pulling matter toward the black hole. On the other hand, there's radiation pressure, pushing matter away. When matter falls toward a black hole and heats up in the accretion disk, it emits radiation. This radiation exerts a pressure on the surrounding matter, pushing it outward. If the black hole tries to accrete matter too quickly, the radiation pressure becomes strong enough to blow the infalling matter away. The matter can't get close enough to cross the event horizon. The accretion rate is limited by this balance. The Eddington limit defines the maximum rate at which a black hole can accrete matter without the radiation pressure overcoming gravity and preventing further infall. For a black hole to grow, it has to accrete matter at or below the Eddington limit. Now, here's where the math gets interesting. If a black hole accretes matter at exactly the Eddington limit, continuously, without stopping, its mass grows exponentially. Specifically, the mass doubles about every 45 million years. This is actually pretty fast by cosmic standards. Start with a stellar mass black hole of, say, 100 solar masses, and let it accrete at the Eddington limit for 1 billion years. After 1 billion years, it would have doubled about 22 times. 2 to the 22nd power is about 4 million, so the black hole would weigh about 400 million solar masses. That's impressive. That's a supermassive black hole, but it's still nowhere near 66 billion solar masses. To reach 66 billion solar masses, starting from 100 solar masses, you'd need the mass to increase by a factor of 660 million. That requires about 29 doublings. At one doubling every 45 million years, that would take about 1.3 billion years. But TON 618 only had 3.4 billion years. So, in principle, if it started as a 100 solar mass black hole and accreted at the Eddington limit continuously for 3.4 billion years, it could reach 66 billion solar masses. Problem solved, right? Not quite. There are several issues with this scenario. First, the Eddington limit assumes a constant supply of matter. The black hole has to have access to an unlimited reservoir of gas and dust to accrete. In reality, as a black hole grows and consumes the matter around it, it depletes the local supply. The accretion rate drops. The black hole enters a quiescent phase, where it's no longer actively consuming matter at a high rate. Most supermassive black holes spend most of their time in these quiet phases, accreting very little. The periods of rapid accretion, when the black hole shines as a quasar, are relatively brief by cosmic standards. Second, the Eddington limit is an average. Some black holes might exceed it temporarily, accreting matter faster than the Eddington limit predicts. This is called super-Eddington accretion. But super-Eddington accretion is unstable. The excess radiation tends to blow away the infalling matter, shutting down the accretion process. It's difficult to sustain super-Eddington accretion for long periods. Third, starting with a 100 solar mass black hole in the early universe is itself problematic. Stellar mass black holes form from the collapse of massive stars. These stars live for only a few million years before exploding as supernovae. So yes, stellar mass black holes could have existed a few 100 million years after the Big Bang. But 100 solar masses is on the high end for a stellar mass black hole. Most are between about 5 and 50 solar masses. Starting with a smaller seed black hole would require even more doublings to reach 66 billion solar masses, and there simply isn't enough time. And finally, even if everything went perfectly, if the black hole started large, if it accreted continuously at the Eddington limit for 3.4 billion years without interruption, if it never ran out of fuel, you'd get to about 66 billion solar masses. But this requires everything to go right. It's like winning the cosmic lottery. And TON 618 isn't the only ultramassive black hole in the early universe. Astronomers have found others, though few as massive. If these black holes were rare flukes, statistical outliers that barely formed under perfect conditions, we might expect to find only one or two. But we've found dozens of supermassive black holes in the early universe, many with masses of billions of solar masses. This suggests that whatever process created these black holes, it wasn't just a lucky accident, it was something more systematic, something that happened relatively commonly in the early universe. And that's the mystery. How did so many black holes grow so massive so quickly? One possibility is that these black holes didn't start as stellar mass black holes. Maybe they started much larger, giving them a head start. In the early universe, conditions were very different from what we see today. Matter was distributed more uniformly, and there were regions of space where enormous clouds of gas, hundreds of thousands or even millions of solar masses, could collapse directly into black holes without ever forming stars first. These are called direct collapse black holes. Under normal circumstances, when a gas cloud collapses, it fragments into smaller pieces, each of which can form a star. This fragmentation is driven by cooling. As the gas collapses, it heats up, and then it radiates that heat away, cooling down. The cooling causes further collapse, and the process continues. Eventually, the cloud breaks up into hundreds or thousands of smaller pieces, each of which becomes a star. But in certain special conditions, if the gas can't cool efficiently, it doesn't fragment. Instead, the entire cloud collapses as a single object, forming a black hole directly. This could happen if the gas is very hot to begin with, or if the cooling mechanisms are suppressed by intense radiation from nearby sources. Some models suggest that direct collapse black holes could form with masses of 10,000, 100,000, or even a million solar masses. If TON 618 started as a direct collapse black hole with, say, 100,000 solar masses, it would only need to double about 10 times to reach 66 billion solar masses. At one doubling every 45 million years, that's only 450 million years, much more feasible. But there's a problem with direct collapse black holes too. They require very specific conditions to form. The gas has to be pristine, free of heavy elements that would enable efficient cooling. It has to be exposed to intense radiation from nearby sources to keep it hot and prevent fragmentation. And it has to be in a region with enough gas to form a massive cloud. These conditions might have existed in the early universe, but it's unclear how common they were. And even if direct collapse black holes formed, it's not clear that they formed frequently enough to explain all the supermassive black holes we see in the early universe. Another possibility is that TON 618 grew primarily through mergers rather than accretion. In the early universe, galaxies were closer together and collided more frequently. When galaxies merge, their central black holes eventually merge too. If TON 618 was in a particularly dense environment, surrounded by other massive black holes, it could have grown rapidly through a series of mergers. Each merger would add mass, and over time, the black hole could reach enormous sizes. But mergers have their own problems. When two black holes merge, they don't just add their masses together. Some mass is converted to energy and radiated away as gravitational waves. This energy loss means that mergers are slightly less efficient than pure accretion at growing black hole mass. More importantly, mergers take time to happen. When two galaxies collide, the black holes don't merge immediately. They have to spiral inward, losing energy through a process called dynamical friction, where gravitational interactions with nearby stars slow them down. This can take hundreds of millions of years. And then, once the black holes get close enough, they emit gravitational waves, which carry away more energy and cause them to spiral even closer. The final merger happens quickly, over the course of a few hours or days, but getting to that point takes a long time. If TON 618 grew primarily through mergers, it would need to merge with hundreds or thousands of other black holes. Each merger takes time to set up and execute. It's hard to see how enough mergers could happen in just 3.4 billion years to produce a 66 billion solar mass black hole. There's one more possibility, one that pushes the boundaries of our understanding even further. Maybe TON 618 represents a fundamentally different kind of object, something that formed in the earliest moments of the universe. Some physicists have theorized about primordial black holes, objects that formed in the first fraction of a second after the Big Bang due to density fluctuations in the fabric of space-time itself. In the immediate aftermath of the Big Bang, the universe was incredibly hot and dense. Tiny variations in density, quantum fluctuations blown up to cosmic scales by the rapid expansion of space, could have led to regions where matter was compressed enough to form black holes. Most primordial black holes, if they exist, would be tiny, smaller than atoms, with masses of only a few grams. These microscopic black holes would have evaporated almost immediately through Hawking radiation. But in certain scenarios, some primordial black holes could have been massive, even supermassive from the very beginning. If TON 618 is a primordial black hole, it could have started with an enormous mass right from the start, bypassing the need for billions of years of growth entirely. It could have been born as a 66 billion solar mass black hole, or close to it, in the first moments after the Big Bang. This is a radical idea, and it's highly speculative. We don't have direct evidence for primordial black holes, and their existence remains a topic of active research and debate among physicists. Some observations, such as the gravitational wave detections from LIGO, hint that primordial black holes might exist, but the evidence is far from conclusive. And even if primordial black holes are real, it's not clear that they can form with the massive sizes needed to explain TON 618. Most theoretical models predict that primordial black holes would be either very small or relatively modest in size, not 66 billion solar masses. So while primordial black holes are an intriguing possibility, they're not a slam-dunk explanation for TON 618. The Eddington limit is a fundamental principle in astrophysics that describes the maximum rate at which a black hole can accrete matter. It's named after Arthur Stanley Eddington, one of the giants of early 20th century astrophysics. Eddington was the astronomer who led the 1919 solar eclipse expedition that provided the first observational confirmation of Einstein's general relativity by PTSE, showing that starlight bends around the sun's mass. He also made fundamental contributions to our understanding of stellar structure and how stars produce energy. The Eddington limit came from his work on stellar physics, but it applies equally well to black holes. The principle is elegantly simple, even if the underlying physics is complex. When matter falls toward a black hole, it doesn't just disappear quietly into the event horizon. It forms an accretion disk, a flat, spinning structure surrounding the black hole. The matter in this disk is in orbit around the black hole, spiraling slowly inward over time. As the matter spirals inward, it moves faster and faster, following Kepler's laws of orbital motion. The closer you are to a massive object, the faster you have to move to maintain orbit. Near a black hole, orbital speeds can reach significant fractions of the speed of light. The different layers of the accretion disk are moving at different speeds. The inner layers are moving faster than the outer layers. This difference in speed creates friction, just like rubbing your hands together creates heat. But this isn't ordinary friction. The speeds are so high, and the energies involved are so enormous, that the friction heats the matter to incredible temperatures. In the accretion disks around stellar mass black holes, temperatures can reach millions of degrees. In the accretion disks around supermassive black holes like TON 618, temperatures can reach billions of degrees. At these temperatures, matter doesn't behave like anything we experience in everyday life. Atoms are torn apart. Electrons are stripped away from nuclei. The material becomes a plasma, a soup of charged particles moving at incredible speeds, and this plasma radiates. It emits light, X-rays, gamma rays, all across the electromagnetic spectrum. The hotter the material, the more energetic the radiation. This radiation doesn't just disappear into space. It has physical effects. Light carries momentum, and when photons, particles of light, strike matter, they push on it. This is called radiation pressure. Under normal circumstances, radiation pressure is negligible. The pressure from sunlight hitting your face on a sunny day is far too weak to notice. But when you're dealing with the intense radiation from an accretion disk around a black hole, radiation pressure becomes significant, very significant. The photons streaming outward from the hot accretion disk slam into the infalling matter, pushing it away from the black hole. At the same time, gravity is pulling the matter toward the black hole. These two forces, gravity pulling inward and radiation pressure pushing outward, are in competition. The Eddington limit is the point where these two forces balance. If the accretion rate is below the Eddington limit, gravity wins. Matter continues to fall inward, crossing the event horizon, adding to the black hole's mass. If the accretion rate tries to exceed the Eddington limit, radiation pressure wins. The outward push from the radiation becomes strong enough to blow away the infalling matter. The matter never reaches the event horizon. It's pushed back out into space, sometimes at high speeds, forming powerful winds and jets. The Eddington limit, therefore, sets a maximum rate for how fast a black hole can grow through accretion. The specific value of the Eddington limit depends on the mass of the black hole. More massive black holes have stronger gravity, which means they can push harder against radiation pressure, allowing for higher accretion rates. But the limit still exists. For a black hole with the mass of the Sun, the Eddington limit corresponds to accreting about 1/10,000,000th of a solar mass per year. That might not sound like much, but over millions of years, it adds up. For a supermassive black hole like Sagittarius A star, with a mass of 4 million suns, the Eddington limit is proportionally higher. It could accrete up to about 0.4 solar masses per year. For TON 618, with its mass of 66 billion suns, the Eddington limit is even higher. But even at the Eddington limit, it takes time to accumulate 66 billion solar masses. Here's the math. If a black hole accretes matter at exactly the Eddington limit, its mass grows exponentially, doubling every 45 million years or so. This is because the Eddington limit scales with mass. As the black hole gets bigger, it can accrete more matter per year, which makes it grow faster, which allows it to accrete even more, and so on. It's a feedback loop. Starting from a stellar mass black hole of, say, 100 solar masses, and assuming continuous accretion at the Eddington limit, you can calculate how long it takes to reach any given mass. To reach 1,000 solar masses, you need about 3.3 doublings, which takes about 150 million years. To reach 1 million solar masses, you need about 13 doublings, which takes about 600 million years. To reach 1 billion solar masses, you need about 23 doublings, which takes about 1 billion years. To reach 66 billion solar masses, you need about 29 doublings, which takes about 1.3 billion years. Now, TON 618 had 3.4 billion years to grow. So, theoretically, if it started as a 100 solar mass black hole and accreted at the Eddington limit continuously for 3.4 billion years, it could reach 66 billion solar masses. The math works out. Problem solved. Except it's not that simple. There are several major issues with this scenario, and each one makes the growth of TON 618 even more mysterious. First, the assumption of continuous accretion at the Eddington limit is unrealistic. In reality, black holes don't accrete steadily. They go through cycles of activity and quiescence. During active phases, they consume matter rapidly and shine brightly as quasars. During quiet phases, they accrete very little and become dim or even invisible except for their gravitational effects. The active phases are relatively short, cosmically speaking. A typical quasar phase might last 10 to 100 million years. Then the black hole runs out of easily accessible fuel, and it enters a quiet phase that can last for hundreds of millions or even billions of years. If TON 618 spent significant amounts of time in quiet phases, not accreting at the Eddington limit, its growth would have been much slower. To reach 66 billion solar masses, it would need to spend almost all of its 3.4 billion years in an active phase, accreting continuously. That's possible, but it seems unlikely. Second, even during active phases, accretion rates often fall below the Eddington limit. The Eddington limit is a theoretical maximum, not a typical value. Most black holes accrete at rates that are a small fraction of the Eddington limit, perhaps 10% or 1%. If TON 618 accreted at 10% of the Eddington limit on average, its doubling time would increase from 45 million years to 450 million years. Over 3.4 billion years, that's only about 7 or 8 doublings. Starting from 100 solar masses, 7 doublings gets you to about 13,000 solar masses. 8 doublings gets you to about 26,000 solar masses. Nowhere close to 66 billion. To reach 66 billion solar masses, while accreting at only 10% of the Eddington limit, you'd need much more time, on the order of 10 to 15 billion years. But the universe was only 3.4 billion years old when TON 618 existed. Third, there's the problem of the seed black hole. Where did that initial 100 solar mass black hole come from? Stellar mass black holes form from the collapse of massive stars. The star has to be at least about 20 to 30 solar masses to form a black hole when it dies. The most massive stars known today are around 200 to 300 solar masses. When these stars explode as supernovae, they leave behind black holes with masses ranging from about 5 solar masses to perhaps 50 or 70 solar masses. Getting a 100 solar mass black hole from a single stellar collapse is difficult. It would require a star more massive than any we've observed. Now, in the early universe, conditions were different. The first stars, called population 3 stars, were likely much more massive than stars forming today. They formed from pristine gas, free of heavy elements, and under these conditions, stars can grow much larger. Some models suggest that population 3 stars could have reached masses of several hundred or even 1,000 solar masses. When these stars died, they might have left behind black holes of 100 solar masses or more. So it's possible that seed black holes in the early universe were larger than typical stellar mass black holes today. But even starting with a 100 solar mass seed, you still need nearly perfect conditions, continuous Eddington limited accretion for over 1 billion years. to reach 66 billion solar masses. And if the seed was smaller, say 10 or 20 solar masses, which is more typical for stellar mass black holes, the problem becomes even worse. Now, here's where things get really interesting. Some astronomers have proposed that TON 618 and other ultramassive black holes in the early universe might have grown through super-Eddington accretion. That is, they might have accreted matter faster than the Eddington limit predicts. On the face of it, this seems impossible. The Eddington limit is based on fundamental physics, the balance between gravity and radiation pressure. How could a black hole exceed this limit? The answer lies in the geometry of the accretion process. The Eddington limit assumes that the radiation escapes spherically, in all directions. But accretion disks aren't spherical, they're flat, and the radiation they produce is often beamed along certain directions, particularly perpendicular to the disk. If the radiation escapes primarily in these directions, along the poles of the black hole, then the radiation pressure pushing on the infalling matter in the disk itself is reduced. Gravity can win, and matter can fall in at rates exceeding the Eddington limit. This is called super-Eddington accretion, and there's some observational evidence that it can happen. Certain objects, called ultraluminous X-ray sources, appear to be accreting at super-Eddington rates. If super-Eddington accretion is possible, it could allow black holes to grow faster than the standard Eddington limit predictions. Maybe TON 618 grew through sustained super-Eddington accretion. But even this has limits. Super-Eddington accretion is unstable. The excess radiation tends to heat up the surrounding gas, creating winds and outflows that blow matter away. It's hard to sustain super-Eddington accretion for long periods. And even if you could, it might speed up growth by a factor of a few, maybe 5 or 10 times faster than Eddington limited growth. That helps, but it doesn't fully solve the problem. To grow from 100 solar masses to 66 billion in 3.4 billion years with only moderately super-Eddington accretion, you'd still need to be lucky. You'd still need a lot of things to go right. Ultimately, the existence of TON 618 and other ultramassive black holes in the early universe is telling us something profound. Either our understanding of black hole growth is incomplete, or these black holes formed in ways we haven't fully considered, or both. Maybe the early universe was more conducive to rapid black hole growth than we realize. Maybe there were mechanisms at play that don't exist today. Maybe the seed black holes were much more massive than we thought. Or maybe, just maybe, TON 618 is something even stranger, something that challenges our understanding of physics in ways we're only beginning to appreciate. One possibility is that TON 618 started much larger than a typical stellar mass black hole. Maybe it didn't begin as the remnant of a single massive star. Maybe it formed through a different process entirely. In the early universe, conditions were very different from what we see today. Matter was distributed more evenly, and there were regions of space where enormous clouds of gas could collapse directly into black holes without ever forming stars. These are called direct collapse black holes, and they could have started with masses of thousands or even hundreds of thousands of suns. If TON 618 began as a direct collapse black hole with, say, 100,000 solar masses, it would have had a significant head start. But even then, growing from 100,000 to 66 billion solar masses in 3.4 billion years requires sustained accretion far beyond what we normally observe. Another possibility is that TON 618 grew through a series of rapid mergers in the early universe. Maybe it was surrounded by an unusually dense environment, a region packed with other massive black holes. As these black holes collided and merged, TON 618 could have grown exponentially. But there's a problem with this theory too. Black hole mergers release gravitational waves, and those gravitational waves carry energy away from the system. Each merger actually results in a slightly smaller combined black hole than the sum of the two original black holes. Some mass is converted to energy and radiated away. So while mergers can help a black hole grow, they're not as efficient as continuous accretion. And even with rapid mergers, getting to 66 billion solar masses in such a short time is extremely difficult. There's another intriguing possibility, one that pushes the boundaries of our understanding even further. Maybe TON 618 represents a fundamentally different kind of object, something that formed in the earliest moments of the universe. Some physicists have theorized about primordial black holes, objects that formed in the first few seconds after the Big Bang due to density fluctuations in the fabric of space-time itself. Most primordial black holes would be tiny, smaller than atoms, but in certain scenarios, some could have been massive, even supermassive from the very beginning. If TON 618 is a primordial black hole, it could have started with an enormous mass right from the start, bypassing the need for billions of years of growth. But this is speculative. We don't have direct evidence for primordial black holes, and their existence remains a topic of active research and debate. What we do know is that TON 618 is not alone. Astronomers have discovered other ultramassive black holes in the early universe, though few as large as TON 618. There's S5000 7+0690, a quasar powered by a black hole weighing about 40 billion solar masses, observed when the universe was only 1.2 billion years old. There's SDSS J0100 +2 802, with a black hole mass of about 12 billion solar masses, also from the very early universe. Each of these discoveries adds to the mystery. How did the universe produce these monsters so quickly? What were conditions like in the early cosmos that allowed such rapid black hole growth? These questions don't have easy answers, and they're forcing astronomers to reconsider fundamental assumptions about how galaxies and black holes evolve. Let's talk about what TON 618 actually looks like, or rather, what we can observe about it. Remember, we can't see the black hole itself. Black holes, by definition, don't emit light. Once something crosses the event horizon, no information about it can ever escape. The black hole is literally a black sphere in space, invisible against the darkness. What we see when we observe TON 618 is not the black hole itself, but the effects it has on its surroundings. Specifically, we see the accretion disk and the jets, the two most dramatic features of an active supermassive black hole. As a quasar, TON 618 is incredibly luminous. When astronomers say something is luminous, they're talking about the total amount of energy it emits per second across all wavelengths of light. The Sun, for example, has a luminosity of about 3.8 times 10 to the 26th watts. That's 380 trillion watts, an almost incomprehensible amount of power. Every second, the Sun radiates enough energy to power human civilization for about 500,000 years. But TON 618 doesn't shine with the light of one sun. It doesn't shine with the light of 1,000 suns, or 1,000,000 suns, or even 1,000,000,000 suns. TON 618 shines with the light of 140 trillion suns. Let me write that out. 140 trillion. That's 140 followed by 12 zeros. In scientific notation, it's about 1.4 times 10 to the 14th solar luminosities. To put this in perspective, the entire Milky Way galaxy, with its 200 to 400 billion stars, shines with the combined light of roughly 25 billion suns. TON 618, a single object, a single black hole and its accretion disk, is about 5,600 times more luminous than our entire galaxy. Think about that. Our galaxy contains hundreds of billions of stars, spread across 100,000 light-years, countless stellar nebulae, glowing clouds of gas lit up by young, hot stars, supernova remnants, the expanding shells of destroyed stars, millions of white dwarfs, the slowly cooling embers of dead stars. All of that combined produces a certain amount of light. TON 618 produces 5,600 times that amount of light, from a region that, while enormous by human standards, is tiny compared to the size of a galaxy. The accretion disk around TON 618 might be a few light-years across at most, probably closer to a few light days or light weeks. For comparison, the Milky Way is 100,000 light-years across. TON 618 is producing 5,600 times the light of the Milky Way from a region that is millions of times smaller. The energy density, the amount of energy per unit volume, is almost beyond calculation. This light comes from the accretion disk. As matter spirals inward toward the black hole, friction heats it to temperatures of millions or even billions of degrees. At these temperatures, the matter emits light across the entire electromagnetic spectrum. Visible light, ultraviolet light, X-rays, gamma rays, all streaming outward into space. The spectrum of light from TON 618 tells us a lot about the conditions in the accretion disk. By analyzing which wavelengths are brightest, astronomers can estimate the temperature of the disk. By studying how the spectrum changes over time, they can learn about variations in the accretion rate. By looking at specific spectral lines, the characteristic patterns created by atoms absorbing or emitting light at particular wavelengths, they can identify which elements are present and how fast they're moving. All of this information paints a picture of a violent, energetic environment. Gas moving at thousands of miles per second. Magnetic fields twisted into complex shapes by the motion of charged particles. Shock waves propagating through the disk, creating regions of extra high temperature and pressure. Turbulence, like atmospheric storms, but on scales larger than entire solar systems. It's chaos, but it's chaos governed by the laws of physics, and by studying it, we can understand how black holes interact with their surroundings. The accretion disk around TON 618 isn't just bright, it's also enormous. The size of an accretion disk depends on several factors, including the mass of the black hole, the amount of matter being accreted, and the angular momentum of that matter. For a black hole as massive as TON 618, the accretion disk could extend for light days or even light weeks from the event horizon. That's still tiny compared to the size of a galaxy, but it's vast by the standards of individual stellar systems. At the inner edge, closest to the event horizon, the disk is hottest and brightest. This is where the matter is moving fastest, experiencing the most intense friction and radiating the most energy. Temperatures here could reach billions of degrees. The radiation is so intense that it ionizes the surrounding gas, stripping electrons from atoms, creating a plasma. Moving outward, the disk gets cooler and dimmer. The outer regions might only be a few thousand degrees, still hot by human standards, but cool compared to the inner disk. The transition from inner to outer disk isn't sharp. It's a gradual change, with temperature and brightness decreasing smoothly as you move away from the black hole. The disk itself is thin, relatively speaking. It might be only a few 100,000 miles thick, tiny compared to its overall diameter of trillions of miles. This thinness is important because it allows the disk to radiate efficiently. If the disk were thicker, the outer layers would trap heat, preventing it from escaping. But a thin disk can radiate heat from both its upper and lower surfaces, keeping it relatively cool and allowing the accretion process to continue. Within the disk, matter is in orbit around the black hole, but these orbits aren't stable forever. Friction and magnetic forces cause the matter to gradually lose angular momentum, spiraling slowly inward. Over time, perhaps over thousands or millions of years, the matter that started at the outer edge of the disk works its way inward, crossing the event horizon and adding to the black hole's mass. From our perspective, watching from 10.4 billion light-years away, we can't see the individual details of the accretion disk. What we see is a single point of light, incredibly bright, with a spectrum that tells us about the conditions in the disk. But even that single point of light is extraordinary. When astronomers first observed TON 618 in the 1950s, they had no idea what they were looking at. The radio emissions were strong, suggesting something powerful was producing them. But the optical light was relatively faint, just a dim blue point in the sky. It wasn't until spectroscopy revealed the enormous redshift that astronomers realized how far away TON 618 was. And once they knew the distance, they could calculate the luminosity. If something appears faint, but is actually very far away, it must be intrinsically bright. The calculation shocked them. TON 618 was producing more light than anything they'd ever observed. It was brighter than entire clusters of galaxies, and it was doing so from what appeared to be a single-point source. What kind of object could produce that much energy? The only explanation that made sense was a supermassive black hole accreting matter at an enormous rate. Nothing else could generate that much power from such a small region of space. Supermassive black holes like TON 618 also produce jets, narrow beams of matter and energy that shoot out from the poles of the black hole at nearly the speed of light. These jets are one of the most spectacular phenomena in the universe, and they're crucial to understanding how black holes interact with their surroundings. Jets form through a complex process involving the accretion disk and the black hole's magnetic field. As matter spirals into the black hole, it's mostly neutral gas at first, but as it heats up in the accretion disk, the atoms are ionized. Electrons are stripped away from nuclei, creating a plasma, a soup of charged particles. Charged particles moving in a magnetic field experience a force that makes them spiral around magnetic field lines. In the intense environment around a black hole, the magnetic fields are incredibly strong and complex. The rotation of the accretion disk twists and amplifies these fields, creating a configuration where field lines are threaded through the disk and extend outward along the rotation axis. Some of the charged particles in the disk follow these field lines, getting funneled toward the poles of the black hole. As they're accelerated along the field lines, they gain energy, eventually reaching speeds close to the speed of light. These relativistic particles shoot outward from the poles, forming two jets, one from each pole, extending in opposite directions. The jets from TON 618 are enormous. They extend for thousands, perhaps millions of light-years into intergalactic space. We know this because we can detect radio emissions from regions far from the quasar itself. When the jet particles collide with intergalactic gas, they transfer energy to that gas, heating it and causing it to emit radio waves. By mapping these radio emissions, astronomers can trace the paths of the jets, seeing how far they extend and how they interact with their environment. In some cases, jets terminate in giant lobes, vast bubbles of hot plasma inflated by the jet material. These lobes can be larger than entire galaxies. They're visible in radio surveys as bright, diffuse regions extending far beyond the host galaxy. For TON 618, the jets would have been incredibly powerful. The amount of energy being channeled into those jets is staggering. Some estimates suggest that jets can carry away up to 10% of the energy released by the accretion process. If TON 618's accretion disk is producing 140 trillion solar luminosities, and 10% of that is going into the jets, that's 14 trillion solar luminosities worth of energy being beamed out into space. That energy doesn't just disappear. It impacts the surrounding environment in profound ways. When the jets collide with intergalactic gas, they heat it to temperatures of millions of degrees. This heated gas can't cool quickly, so it remains hot and diffuse, unable to collapse and form new stars. In this way, jets from supermassive black holes like TON 618 suppress star formation, not just in their host galaxies, but across vast regions of intergalactic space. This process, called feedback, is crucial to understanding why galaxies have the properties they do. Without feedback from black holes, galaxies would convert most of their gas into stars very quickly, leaving behind galaxies that are more massive and more metal-rich than what we observe. The feedback regulates star formation, ensuring that galaxies grow at a measured pace. Jets also create structure in the intergalactic medium. Before jets carve through the gas, it's relatively uniform, smoothly distributed across space. After a jet passes through, it leaves behind cavities, regions where the gas has been pushed aside. It also creates shock fronts, boundaries where the fast-moving jet material collides with stationary gas. These shock fronts can trigger star formation in some cases, compressing the gas enough that it collapses and forms stars. So jets can both suppress and trigger star formation, depending on the specific conditions. The jets from TON 618 would have shaped the early universe in significant ways. 10.4 billion years ago, when TON 618 was shining as a quasar, the universe was younger and denser. Galaxies were closer together. Intergalactic gas was more abundant. The jets from TON 618 would have reached out across millions of light years, heating gas, creating shock waves, influencing the formation of galaxies in a huge volume of space. In a sense, TON 618 wasn't just a black hole sitting passively in space. It was an active participant in cosmic evolution, reshaping its corner of the universe, determining which galaxies could form and which couldn't. The reach of its influence extended far beyond the galaxy hosting the black hole, and it wasn't alone. There were other quasars in the early universe, other supermassive black holes producing jets and feedback. Together, these objects played a major role in determining the large-scale structure of the universe, the distribution of galaxies and gas that we see today. Now, here's a fascinating detail about jets. They're not continuous beams. They're more like a stream of blobs, discrete clumps of material moving at near light speed. High-resolution radio observations of jets reveal this structure, showing bright knots moving along the jet's path. These knots are created by instabilities in the jet flow. As the jet material streams outward, small perturbations can grow, creating regions of higher and lower density. The high-density regions, the knots, are brighter because they contain more particles emitting radiation. By tracking the motion of these knots over time, astronomers can measure how fast the jet material is moving. In many cases, the knots appear to be moving faster than the speed of light. This is an illusion, a consequence of special relativity. If a jet is moving almost directly toward you, at close to the speed of light, the material it emits at different times reaches you at nearly the same time. This compresses the observed motion, making it appear faster than it actually is. The effect is called superluminal motion, and it's a clear sign that jet material is moving at relativistic speeds. For TON 618, we don't have detailed enough observations to track individual knots in the jets. The quasar is too far away, and the jets are seen from an angle that makes superluminal motion less apparent. But based on what we know about other quasars, it's almost certain that the jets from TON 618 are moving at speeds of 90% or more of the speed of light. At these speeds, relativistic effects become important. Time dilation means that clocks moving with the jet material tick more slowly than clocks at rest. Length contraction means that distances along the direction of motion are compressed, and the energy required to accelerate matter to these speeds is enormous. It takes a supermassive black hole, with its immense gravitational energy and powerful magnetic fields, to create jets like this. Nothing less could do it. Another interesting feature of jets is that they can bend and curve as they propagate through space. If the intergalactic medium isn't uniform, if there are regions of higher or lower density, the jet can be deflected. In some cases, jets produce spectacular C-shaped or S-shaped structures, curving back on themselves. These curved jets tell us about the motion of the host galaxy. If the galaxy is moving through intergalactic gas, the gas acts like a wind, pushing on the jets and bending them backward. It's similar to how smoke from a moving train gets swept backward by the wind. By studying the shape of the jets, astronomers can learn about the velocity of the galaxy and the properties of the intergalactic medium. For TON 618, the jets likely extend for millions of light years, creating vast radio lobes that dwarf the host galaxy. These structures would have been visible to radio telescopes across a significant fraction of the observable universe. In fact, it's likely that the jets from TON 618, or the remnants of those jets, still exist today. The radio emission we detect from TON 618 is from 10.4 billion years ago. But the jets have been propagating outward since then. Even if the quasar has shut down, if TON 618 is no longer actively accreting matter, the jets it produced in the past would still be traveling through space. At near light speed, in 10.4 billion years, those jets would have traveled 10.4 billion light years or more from their source. Of course, we can't see the present-day state of TON 618. The light from today won't reach us for another 10.4 billion years. But it's fascinating to think that somewhere out there, billions of light years away, the remnants of those ancient jets are still making their way through intergalactic space, a legacy of a time when TON 618 was one of the brightest objects in the universe. Now, let's talk about what it would be like to approach TON 618. This is, of course, a thought experiment. There's no spacecraft that could survive such a journey, and even if there were, the trip would take billions of years at any realistic speed. But it's worth imagining because it helps us understand the scale and power of this object. Imagine you're in a spacecraft, somehow capable of traveling faster than light, heading toward TON 618. At first, from billions of light years away, TON 618 appears as nothing more than a bright point of light, indistinguishable from a star. You're seeing the quasar, the brilliant accretion disk, but at this distance, it's just a dot. As you travel closer, covering billions of light years, that dot slowly grows brighter. At 1 billion light years away, TON 618 is noticeably brighter than anything else in your sky. It's still a point source. You can't resolve any structure, but it's unmistakably bright. If you were to measure the spectrum of that light, you'd find it shifted toward the blue end of the spectrum because you're moving toward the source. This is the opposite of the redshift caused by the expansion of the universe. At 100 million light years, the brightness is almost overwhelming, even though you're still incredibly far away. TON 618 is now outshining entire clusters of galaxies. If you looked around at the universe from this distance, you'd see galaxies, some nearby, some far away, but TON 618 would be brighter than almost anything else in view. You might start to notice that the light isn't just bright, it's also energetic. Instruments on your spacecraft would detect high-energy photons, ultraviolet light, X-rays, even gamma rays streaming from the quasar. At 10 million light-years, you're now closer to TON 618 than we are to the Virgo cluster, the nearest large cluster of galaxies to the Milky Way. The brightness is extraordinary. If there are any galaxies in the vicinity, they're completely outshone by the quasar. The sky is dominated by this single point of light. You begin to see the structure of the system. The jets, those colossal beams of energy, extend outward from the core, visible now as faint lines of radio emissions stretching for millions of light-years in opposite directions. You might notice the effects of the jets on the surrounding intergalactic gas. Huge bubbles of hot plasma, heated by the jet material, glow faintly in X-rays. The environment is hostile. The radiation levels are starting to become dangerous. Your spacecraft's shielding is working, but you can feel, figuratively, the intensity of the energy in this region. At 1 million light-years, you're experiencing something few objects in the universe ever experience. You're close enough to Ton 618 that its gravitational influence is starting to affect you. The pull is still relatively weak, negligible compared to the gravity of nearby stars or gas clouds, but it's there. More importantly, the radiation is lethal. High-energy particles streaming from the accretion disk and jets are bombarding your spacecraft. Even with advanced shielding, exposure to this environment for more than a few minutes would be fatal to any biological organism. The electronics on your spacecraft are starting to malfunction. Radiation is causing errors in computer systems, flipping bits, corrupting data. You're closer to Ton 618 than we are to the Andromeda Galaxy. But the conditions couldn't be more different. Andromeda is quiet, peaceful, a majestic spiral galaxy drifting through space. Ton 618 is a maelstrom, a cosmic hurricane of energy and matter. At 100,000 light-years, you're now roughly as far from Ton 618 as we are from the center of our own galaxy. But the similarities end there. The light from Ton 618 fills your field of view. It's no longer a point source. You can start to resolve structure. The accretion disk, though still too small to see individual features, is beginning to appear as a tiny disk rather than a point. The brightness is beyond anything you can imagine, even through heavy filters. Looking at Ton 618 is blinding. The temperature outside your spacecraft is rising. Not because there's air to heat up, space is still a vacuum, but because the radiation is so intense that any surface exposed to it absorbs energy and heats up. Materials that were once cool are now glowing red-hot. At 10,000 light-years, the situation is desperate. Your spacecraft is failing. The radiation has overwhelmed the shielding. Systems are shutting down. The heat is unbearable. You can see the accretion disk clearly now. It's a glowing, swirling structure, impossibly bright, impossibly large. You can see variations in brightness, brighter regions where the disk is hotter, darker lanes where magnetic fields or density variations create cooler areas. The light is so intense that it's ionizing the sparse gas around you. Atoms are being stripped of their electrons, creating a diffuse glow. You're inside a bubble of plasma, heated by the radiation from Ton 618. At 1,000 light-years, the gravitational effects become unmistakable. Space-time itself is warped by the immense mass of Ton 618. Distances don't make sense anymore. Objects that should be a certain distance away appear stretched or compressed. Light traveling through this region is bent, creating strange visual effects. You might see multiple images of distant stars, their light bent by the gravity into different paths that all reach your eyes. This is gravitational lensing on a scale you've never experienced. Your spacecraft, if it's still functional at all, is being pulled inward. There's no escaping now. The gravity is too strong. Even at full thrust, you can't overcome the pull. You're falling toward Ton 618, accelerating, moving faster and faster. At 100 light-years, time begins to behave strangely. Clocks on your ship, if they're still working, are running noticeably slower than clocks far from the black hole. If you could somehow send a signal back to a safe location far away, the people there would receive your messages at an increasingly delayed rate. This is time dilation, a consequence of the intense gravitational field. The stronger the gravity, the slower time passes. The accretion disk dominates your entire field of view. You're surrounded by light, by radiation, by energy. The temperature outside your ship is millions of degrees. If your spacecraft somehow survived this long, it's not surviving now. The materials are vaporizing, turning into plasma, joining the accretion disk. You're no longer in a spacecraft. You're a stream of atoms, falling toward the black hole. At 10 light-years, you're deep inside the region where the black hole's gravity is the dominant force. Nothing in the universe can save you now. You're part of the accretion disk, spiraling inward, heated by friction, emitting light and radiation. You've become part of what makes TON 618 so bright. At 1 light-year, about 6 trillion miles, you're moving at a significant fraction of the speed of light. The material around you is orbiting at similar speeds. Collisions are frequent. The energy released by these collisions is enormous. You're contributing to the light that astronomers billions of light-years away will see as a bright quasar. At 0.1 light-years, about 630 billion miles, the event horizon is starting to come into view. Not as a physical thing, but as a boundary. Light emitted just inside the event horizon never escapes. It's bent back toward the singularity by the gravity. From your perspective, the event horizon appears as a perfect black circle, darker than anything you've ever seen, surrounded by the glowing accretion disk. It's a hole in space, a boundary beyond which information cannot return. At 0.01 light-years, about 63 billion miles, you're experiencing extreme tidal forces. The side of your atomic stream that's closer to the black hole is being pulled harder than the side farther away. This difference, small at first, is growing rapidly as you fall inward. This is spaghettification, the stretching of objects into long, thin shapes by tidal forces. It's the inevitable fate of anything that falls into a black hole, regardless of size. At 1 billion miles, you're inside the accretion disk itself. The material around you is moving at incredible speeds, colliding, fusing, releasing energy. The conditions are indescribable. Temperatures, densities, energies beyond anything found anywhere else in the universe except near other black holes or in the moments after the Big Bang. At 100 million miles, you can see the event horizon clearly. It's not a physical surface, but a boundary, a point of no return. From the outside, an observer watching you would see you appear to slow down, freeze, and redshift as you approach the horizon. You'd appear to take forever to cross it, asymptotically approaching but never quite reaching. But from your perspective, you cross the event horizon in finite time. There's no barrier, no sensation of crossing. One moment you're outside, the next you're inside. But now, there's no going back. At 10 million miles, you're past the event horizon. You're inside the black hole. Every direction you look, every path you could take, leads toward the singularity. The concept of space and time have switched roles in a way that's hard to describe. Just as you previously couldn't help but move forward in time, you now can't help but move toward the singularity. It's not a place in space anymore. It's a moment in your future, as inevitable as tomorrow. At 1 million miles, the tidal forces are beyond catastrophic. Even individual atoms are being stretched. The bonds holding molecules together, if any existed at this point, are shattered. At 100,000 miles, you're approaching the singularity. Our understanding of physics breaks down here. General relativity predicts that the singularity is a point of infinite density, where all the mass of the black hole is concentrated. But we don't really know what happens. Quantum mechanics should play a role, but we don't yet have a theory that combines quantum mechanics and general relativity in a consistent way. We don't have a theory of quantum gravity, and then you reach the singularity. What happens next is unknown. Does matter cease to exist? Is it crushed into some exotic form we can't comprehend? Is information preserved somehow, encoded in subtle correlations that we can't currently detect? Do you emerge somewhere else, in another universe perhaps, through a hypothetical wormhole? We don't know. The singularity is where our physics ends, where our ability to predict and explain the universe reaches its limit. It's the ultimate mystery, the final frontier of our understanding. But let's step back and think about TON 618 from a different perspective. What does it mean for the universe that such objects exist? Supermassive black holes like TON 618 aren't just cosmic oddities. They're fundamental to the structure and evolution of the universe. In the early cosmos, the first black holes likely formed from the collapse of massive stars, just a few 100 million years after the Big Bang. These stellar mass black holes began pulling in surrounding gas, growing larger. As they grew, they started to influence the galaxies forming around them. The relationship between supermassive black holes and their host galaxies is surprisingly intimate. Observations have shown that the mass of a galaxy's central black hole is closely related to the mass of the galaxy's bulge, the dense concentration of stars at the center. This suggests that black holes and galaxies grow together, evolving in tandem over billions of years. The energy released by accreting supermassive black holes, in the form of radiation and jets, can heat the gas in and around galaxies, preventing it from cooling and collapsing to form new stars. This process, called feedback, regulates star formation and prevents galaxies from growing too large. Without supermassive black holes, galaxies would look very different. They might be much larger, packed with more stars, but potentially less stable. The feedback from black holes helps to sculpt the galaxy population we observe today. TON 618, as one of the earliest and most massive black holes, played a significant role in shaping its corner of the universe during the first few billion years after the Big Bang. Its jets and radiation would have influenced the formation of galaxies across millions of light years. It's a reminder that black holes, despite being dark and invisible, are some of the most powerful and influential objects in the cosmos. There's another fascinating aspect of TON 618 that we haven't discussed yet. Because it's so far away, and because light takes time to travel, we're seeing TON 618 as it was 10.4 billion years ago. What is TON 618 doing right now, today, in the present moment? We don't know. We won't know for another 10.4 billion years, when the light from present-day TON 618 finally reaches us. It's possible that TON 618 is still active, still consuming matter, still shining as a brilliant quasar. Or it might have quieted down, exhausted the supply of gas in its surroundings, and entered a dormant phase. Many supermassive black holes go through cycles of activity and quiescence. During active phases, they accrete matter rapidly and shine brightly. During quiet phases, they sit dormant, invisible except for their gravitational effects. Sagittarius A star, the black hole at the center of our galaxy, is currently in a quiet phase. It's not consuming much matter, and it's relatively dim compared to what it could be. But there's evidence that Sagittarius A star was much more active in the past. Huge bubbles of gamma-ray emission, called the Fermi bubbles, extend above and below the plane of the Milky Way, likely created by a burst of activity from Sagittarius A star millions of years ago. TON 618 might follow a similar pattern. It could be in a phase of intense activity now, 10.4 billion years ago from our perspective, and might have calmed down in the billions of years since. Or it could still be raging, consuming matter, shining brightly. We simply can't know until enough time has passed for the light to reach us. This is one of the strange realities of astronomy. When we observe distant objects, we're not just looking through space, we're looking back in time. The universe is a time machine, showing us the past, written in light. Let's consider one more mind-bending aspect of TON 618. What would happen if you fell into it? We touched on this earlier, but let's go deeper into the physics. As you approach the event horizon, two main effects dominate: tidal forces and time dilation. Tidal forces arise because gravity weakens with distance. The side of your body, closer to the black hole, feels stronger gravity than the side farther away. For a small black hole, this difference is extreme, even far from the event horizon. You'd be ripped apart long before you reach the event horizon. But TON 618 is so large that the tidal forces at the event horizon are actually relatively mild. The event horizon is so far from the singularity that the gradient in gravitational force across your body would be small. You could, in theory, cross the event horizon intact, without immediately being torn apart. This is counterintuitive. A larger black hole is actually less dangerous at the event horizon than a smaller one, at least in terms of tidal forces. But time dilation is unavoidable. As you fall toward the event horizon, time for you continues normally. But from the perspective of an outside observer, you appear to slow down, freeze, and fade as you approach the horizon. This is because the light from you takes longer and longer to escape the strong gravitational field. Eventually, the light is so shifted to longer wavelengths, that it becomes invisible. From the outside, you appear to freeze at the event horizon forever. But from your perspective, you cross the horizon in a finite amount of time. Once inside, you're doomed. You can't escape. You can't even stay still. The singularity is in your future, as inevitable as tomorrow. And as you approach the singularity, the tidal forces do become extreme, even for a black hole as large as TON 618. At some point, you're torn apart, spaghettified, reduced to a stream of atoms falling toward the singularity. What happens at the singularity itself is a mystery. General relativity breaks down. The equations produce infinities, nonsensical results. We need a theory of quantum gravity to understand what really happens, but we don't have one yet. Some physicists think the singularity might not be a point of infinite density, but rather a region where space and time behave in ways we can't currently describe. Others suggest that information falling into a black hole might not be lost, but encoded somehow on the event horizon or released through Hawking radiation over time. These are deep, unresolved questions that sit at the frontier of theoretical physics. Let's zoom out and think about the bigger picture. TON 618 is the largest black hole we've found so far. But is it the largest that can exist? Is there a theoretical maximum size for a black hole? Interestingly, there might be. As a black hole grows, it affects its environment more and more dramatically. The radiation from its accretion disk becomes so intense that it blows away the surrounding gas, limiting further growth. The jets become more powerful, heating intergalactic gas over vast regions. At some point, the black hole becomes so disruptive that it can't accrete matter efficiently anymore. It's killed its own food supply. Theoretical models suggest that there's a practical upper limit for supermassive black holes, somewhere in the range of 50 to 100 billion solar masses. TON 618 is right at the edge of this range. It's possible that black holes simply can't grow much larger than this because they become too efficient at preventing further accretion. But nature has a way of surprising us. Maybe there are even larger black holes out there, hiding in the distant universe, waiting to be discovered. Or maybe TON 618 represents the extreme limit, the largest monster the universe can produce. Another question worth pondering is what TON 618 tells us about the fate of the universe. Black holes are the ultimate survivors. Stars die, galaxies fade, but black holes endure. In the far future, trillions of years from now, when the last stars have burned out and the universe has grown cold and dark, black holes will be among the last objects remaining. They'll slowly evaporate through a process called Hawking radiation, releasing tiny amounts of energy over unimaginable timescales. For a black hole the size of TON 618, the evaporation time is almost incomprehensible. It would take something like 10 to the power of 100 years, a 1 followed by 100 zeros, for TON 618 to evaporate completely. For context, the universe is currently about 10 to the power of 10 years old, 13.8 billion years. The time it takes for TON 618 to evaporate is 10 to the 90 years longer than the current age of the universe. It's a timescale so vast that it makes the entire history of the cosmos, from the Big Bang to now, seem like the blink of an eye. By the time TON 618 finally evaporates, the universe will be unrecognizable. All matter will have decayed, all stars will be gone, and the universe will be cold, dark, and nearly empty, approaching what's sometimes called the heat death. And yet, even in that distant future, black holes like TON 618 will still be there, slowly fading, but enduring far longer than anything else. It's both haunting and awe-inspiring to think about. Let's talk about some of the other extreme black holes that have been discovered, just for context. Phoenix A, a black hole at the center of the Phoenix cluster, weighs about 100 billion solar masses, making it potentially larger than TON 618, though the mass estimate is less certain. IC 10101, another ultramassive black hole, is estimated at around 40 billion solar masses. These monsters are rare, but they exist, scattered across the universe, each one a testament to the extreme physics of the early cosmos. Interestingly, most of the largest black holes are found in the early universe, similar to TON 618. This suggests that conditions in the early cosmos were uniquely suited to the rapid growth of supermassive black holes. As the universe aged, galaxies settled into more stable configurations, and the rate of black hole growth slowed. Today, most supermassive black holes are in quiet phases, no longer actively consuming vast amounts of matter, but in the early universe, it was a different story. Gas was plentiful, galaxies were colliding and merging frequently, and black holes had ample fuel to grow to enormous sizes. TON 618 is a relic from that chaotic era, a survivor from a time when the universe was young, violent, and full of potential. One of the most exciting aspects of studying objects like TON 618 is what they can teach us about the fundamental laws of physics. Black holes are natural laboratories for testing general relativity in extreme conditions. The gravity near a supermassive black hole is so intense that space and time are warped in ways that don't occur anywhere else. By observing the behavior of matter and light around these black holes, astronomers can test Einstein's predictions and look for deviations that might hint at new physics. So far, general relativity has passed every test with flying colors. The observations match the predictions remarkably well. But there are still mysteries. The singularity, the nature of the event horizon, the information paradox, all of these point to gaps in our understanding. Quantum mechanics tells us that information can't be destroyed, but black holes seem to destroy information by swallowing it. This paradox has puzzled physicists for decades. Stephen Hawking famously proposed that black holes emit radiation, now called Hawking radiation, and that this radiation might carry information about what fell into the black hole. But the details of how this works are still unclear. TON 618, as one of the most extreme black holes known, is a prime target for studying these questions. Future observations, with more powerful telescopes and instruments, might reveal new details about how matter behaves in such extreme conditions. Maybe we'll find evidence of quantum effects at the event horizon, or signatures of physics beyond general relativity. Or maybe TON 618 will continue to confirm what we already know, reinforcing our confidence in Einstein's theory. Either way, the study of black holes like TON 618 is pushing the boundaries of human knowledge, taking us closer to understanding the true nature of reality. Let's return to the question that started this journey. How did TON 618 get so big so fast? We've explored several possibilities: direct collapse black holes, rapid mergers, primordial black holes, super-Eddington accretion, but none of them fully explain it. The truth is, we don't have a complete answer yet, and that's okay. Science is a process, not a destination. Each discovery, each observation, brings us closer to understanding, even if it also raises new questions. TON 618 is a challenge, a puzzle that doesn't fit neatly into our current models. But challenges like this are what drive science forward. They force us to reconsider our assumptions, to develop new theories, to push the boundaries of what we know. In the coming years, new telescopes like the James Webb Space Telescope and the Extremely Large Telescope will allow us to study the early universe in unprecedented detail. We'll be able to observe more distant quasars, more massive black holes, and hopefully find clues that help us solve the mystery of TON 618. Maybe we'll discover that the early universe was even stranger than we thought, with conditions that allowed for rapid black hole growth in ways we haven't imagined. Or maybe we'll find that TON 618 is an outlier, a one-in-a-billion fluke that happened to form under just the right circumstances. Whatever the answer turns out to be, the journey to find it will be fascinating. Before we wrap up, let's take a moment to appreciate just how extraordinary TON 618 really is. In a universe filled with wonders, with galaxies and stars and nebulae, with planets and moons and comets, TON 618 stands out as something truly special. It's a reminder of the sheer scale and power of the cosmos, of forces and energies beyond human comprehension. It's a testament to the beauty of physics, to the elegance of general relativity, to the way mathematics can describe the most extreme phenomena in the universe. And it's a humbling reminder of our place in the cosmos. We're tiny, fragile beings, living on a small planet orbiting an average star in an ordinary galaxy, and yet we've managed to discover and study an object like TON 618, located billions of light-years away, existing in a time when the universe was less than a quarter of its current age. That's an incredible achievement, a testament to human curiosity, ingenuity, and the power of science. We've built telescopes that can see across the universe. We've developed theories that can explain the behavior of black holes. We've sent probes to other planets, landed robots on Mars, and even sent humans to the moon. And we're just getting started. The next few decades will bring even more discoveries, even more insights into the nature of the universe. We'll learn more about black holes, about dark matter and dark energy, about the origin and fate of the cosmos. We'll push the boundaries of what's possible, exploring new frontiers, answering old questions, and uncovering new mysteries. And objects like TON 618 will be our guides, beacons of light from the distant past, helping us understand the universe we live in. So tonight, as we conclude this journey into the heart of the largest black hole in the universe, let's take a moment to reflect on what TON 618 really means. It's more than just a massive object, more than just a record holder in some cosmic census. TON 618 is a window into the early universe, a glimpse of a time when the cosmos was young, chaotic, and full of potential. It's a test of our theories, pushing the boundaries of what we thought was possible, forcing us to reconsider our assumptions about how black holes form and grow. It's a challenge to our understanding, a puzzle that doesn't fit neatly into our models, demanding that we think deeper, work harder, and develop new ideas. And it's a reminder, a humbling, awe-inspiring reminder that the cosmos is vast, mysterious, and full of wonders we're only beginning to comprehend. When we look at TON 618, we're not just seeing a black hole. We're seeing the consequences of gravity taken to its extreme. We're seeing what happens when matter collapses under its own weight to such a degree that it tears a hole in the fabric of space-time. We're seeing the interplay between matter and energy, between gravity and radiation, between the largest structures in the universe and the smallest quantum fluctuations. We're seeing a cosmic laboratory where the laws of physics are tested in conditions that don't exist anywhere else, conditions so extreme that our current theories struggle to describe them. And through all of this, we're learning. We're learning about the universe. We're learning about the fundamental forces that govern reality. We're learning about the limits of our knowledge and where those limits lie. Every observation of TON 618, every measurement of its mass or luminosity or redshift adds a piece to the puzzle. Slowly, gradually, we're building a more complete picture of how the universe works. TON 618 also reminds us of our place in the cosmos. We're tiny, fragile beings, living on a small planet orbiting an average star in an ordinary galaxy. Our entire existence, from the dawn of humanity to the present day, spans only a few 100,000 years. In cosmic terms, we've barely existed at all. The light we see from TON 618 left that object 10.4 billion years ago, long before our sun even formed, long before our planet existed, long before life arose on Earth. And yet, despite our insignificance in terms of size and age, we've managed to discover TON 618. We've measured its mass, calculated its distance, studied its properties. We've built telescopes that can see across the universe, instruments that can detect the faintest signals from the most distant objects. We've developed theories that explain the behavior of black holes, equations that describe the curvature of space-time, models that predict the evolution of the cosmos. That's an incredible achievement. It's a testament to human curiosity, to our drive to understand, to our refusal to accept ignorance when knowledge is within reach. We're explorers, scientists, thinkers, dreamers, and we're just getting started. The study of TON 618 is far from over. In the coming years and decades, new telescopes and instruments will give us even more detailed views of this and other supermassive black holes. The James Webb Space Telescope, launched in 2021, is already providing unprecedented views of the early universe. It's detecting galaxies and quasars from even earlier times, pushing back the frontier of our knowledge. The extremely large telescope, currently under construction in Chile, will have a mirror over 39 meters in diameter. It will be able to study the environments around distant black holes in exquisite detail, resolving features that are currently invisible. Future gravitational wave observatories, both on Earth and in space, will detect the mergers of supermassive black holes, giving us direct evidence of how these giants collide and combine. And new theoretical work, combining insights from quantum mechanics, general relativity, and cosmology, will help us understand the processes that created TON 618 and other ultramassive black holes in the early universe. Maybe we'll discover that direct collapse black holes are more common than we thought. Maybe we'll find evidence of super-Eddington accretion in action, watching black holes grow faster than the Eddington limit predicts. Maybe we'll even find primordial black holes, objects born in the first moments after the Big Bang, confirming one of the more speculative ideas about how supermassive black holes form. Or maybe we'll find something completely unexpected, something that forces us to rethink everything we thought we knew. That's the beauty of science. Every answer raises new questions. Every discovery opens new avenues of inquiry. TON 618 is a milestone, but it's not the end of the road. It's a stepping stone, a point along the journey of discovery that will continue for as long as humans are curious about the universe. And let's not forget the sheer wonder of it all. TON 618 is terrifying in its size and power. Yes, it's a cosmic monster, a force of nature so immense that it challenges our ability to comprehend it. But it's also beautiful. There's elegance in the mathematics that describes black holes, beauty in the way general relativity predicts their properties, wonder in the realization that such objects exist. The universe didn't have to be this way. It didn't have to produce black holes at all. The laws of physics could have been different, the constants of nature could have had different values, and black holes might never have formed. But they did. The universe created black holes, and in doing so, it created some of the most extreme, most fascinating, most awe-inspiring objects imaginable. TON 618 is one of those objects, a crown jewel in the cosmic collection, a masterpiece of nature, and we get to study it. We get to marvel at it. We get to try to understand it. So as we wrap up this exploration, I want to leave you with a thought. The universe is bigger, stranger, and more wonderful than we ever imagined. Objects like TON 618 exist, defying our expectations, challenging our theories, inspiring our curiosity. And there are countless more mysteries waiting to be discovered, more black holes, perhaps even larger than TON 618, more galaxies, more stars, more planets, maybe even life, somewhere out there in the vastness of space. The universe is an open book, and we're still reading the first few chapters. Every discovery, every observation, every new insight brings us closer to understanding the grand story of the cosmos. And that story is still being written. TON 618 is just one chapter in that story, but what a chapter it is. A black hole so massive, so impossibly large, that it defies explanation. A cosmic monster that shouldn't exist according to our current models, but does. A window into the early universe, a time when the cosmos was young and violent and full of energy. A challenge to our understanding, a puzzle that demands new ideas and new theories. And a source of wonder, a reminder that the universe is capable of producing things beyond our wildest imaginations. In studying TON 618, we're not just learning about black holes. We're learning about ourselves, about what it means to be human, about our place in the vast cosmic tapestry. We're tiny, yes, but we're also mighty. We're curious, intelligent, capable of asking questions and finding answers. We're explorers, venturing into the unknown, seeking to understand the universe around us. And in that quest for understanding, we find meaning, purpose, beauty. So thank you for joining me on this journey tonight. Thank you for your curiosity, your willingness to explore the unknown, your appreciation for the beauty and mystery of the cosmos. The universe is waiting, full of wonders we've yet to discover, and there's so much more to explore. Until next time, keep looking up, keep asking questions, and never stop wondering, because the greatest discoveries are still ahead of us. The universe has secrets yet to reveal, mysteries yet to solve, wonders yet to find, and who knows, maybe one day we'll discover something even more incredible than TON 618. Something that will once again force us to reconsider everything we thought we knew. Something that will expand our understanding of the cosmos in ways we can't currently imagine. That's the promise of science, the thrill of discovery, the joy of exploration. There's always something new on the horizon, always another question to ask, always another mystery to unravel. And that's what makes this journey so worthwhile. That's what makes the study of the universe so endlessly fascinating. We'll never run out of things to discover, never exhaust the wonders of the cosmos. As long as we keep looking, keep questioning, keep exploring, there will always be more to find. Good night.